Hello, my name is Brad Elkins. I'm a technical sales manager with EOS Remediation, and I'll be presenting a topic today titled Management of Aquifer pH with an Alkaline Colloidal Suspension. The focus of my talk will be on adjusting and controlling pH for in situ bioremediation of chlorinated solvents. To get started, let's define a couple of terms, pH and acidity. pH is simply just the negative log of the H ion, whereas acidity is the amount of either base or acid needed to raise or lower the pH of a system by 1 standard unit. So that just because a system has a high acidity doesn't necessarily mean it has a low pH, and this is demonstrated by the graph below. I'm comparing hydrochloric acid and acetic acid, and as you can see, the hydrochloric acid has a much lower starting pH. But the amount of sodium hydroxide that's required to shift the pH of that system for the hydrochloric acid is half the amount as it takes to shift the pH of the acetic acid environment. So while hydrochloric acid might have a lower starting pH, it technically has a lower acidity value. It doesn't take as much base to move the pH of that system. Why should you care about pH? What's the importance of pH? Well, in regards to our remedial efforts, it's important to understand that pH can impact the cation exchange capacities of certain lithologies, especially ones that are high in silt and clay material. But for certain contaminants, you can control the dissolutions, so something like metals or radionuclides, you can either mobilize or precipitate these compounds by shifting the pH of the system. You can also promote alkaline hydrolysis of certain explosives like RDX and TNT. Finally, and the majority of my talk will focus on this topic, and that is the pH of the system can inhibit and dictate the bioactivity of certain microorganisms in the subsurface. It's well documented that D. halicoides is sensitive to pH, whether it's an acidic pH or an alkaline pH. And there's a certain window, about a 5.5 to 8 range, that D. halicoides likes to live in to get good degradation. So maintaining that pH or shifting the system to that pH is critical to have a successful remedial strategy. So let's talk about bioremediation. So in a nutshell, bioremediation is simply providing an electron donor and an electron acceptor in an aqueous environment, and microorganisms are going to utilize that electron donor to then respire or break down a contaminant of concern. And here I'm showing a chlorinated solvent, PCE going to TCE. And there's two mechanisms at play. The first one is fermentation, and so that's where you actually break down whatever substrate you've introduced into the subsurface, and in this case I'm showing EOS, or emulsified vegetable oil. That's fermented and it releases molecular hydrogen. It is actually the molecular hydrogen that is the electron donor, and the bug can utilize this, removing one of the chlorines and replacing it with a hydrogen. And when they do this, that's where they're getting their energy from to multiply and produce waste and carry on. And by this action, they're degrading the contaminant, and so that would be respiration. So taking that hydrogen, replacing it with a chlorine, that's respiration and bioremediation. Now this process isn't necessarily limited to the subsurface. Every living organism on the planet does this. You and I do this every day. Electron donor for us would be something like a cheeseburger, and our electron acceptor would be the oxygen that we're breathing from the atmosphere. But the process, both processes, both fermentation and respiration, produce acidity in the system. Here I'm showing sodium lactate and soybean oil, and when you ferment these, they release molecular hydrogen, but they also release some acidity. And it's not limited to just sodium lactate or soybean oil. Pretty much any organic substrate that you introduce into the subsurface that can ferment will produce some acidity. And here I'm showing in this table several common organic substrates that are used for enhanced in situ bioremediation, and the ratio of acidity to molecular hydrogen production. What you would want is a substrate that would produce relatively low acidity but give you the amount of hydrogen that you need to properly dechlorinate the contaminant. And so you can see here that while sodium lactate, which is the second one from the left-hand side of the table, has a nice low acidity to molecular hydrogen ratio, when you look at the balanced equation at the top, you see that you're really only getting 6 moles of molecular hydrogen. Whereas when you look at soybean oil, you're getting that same low ratio of acidity to molecular hydrogen, but you're releasing 156 moles of molecular hydrogen for that acidity. So you're getting much more bang for your buck. Next is respiration. So the actual mechanism by which we're degrading the contaminant, you're producing acid. Theoretically, if you degrade 1 mole of PCE, you will form 4 moles of hydrochloric acid. The last thing to be concerned about in regards to pH is the prevailing conditions. And here I'm showing a map from the USGS, and this is depicting soil pH across the United States. And so the blue and yellow colors are going to be more alkaline pHs, so something around 8, whereas the oranges and reds are going to be more acidic pHs, so probably around 4, 4.5. And you can see that the southeast and much of the northeast is pretty much dominated by acidic conditions. And while you can't necessarily correlate in every case acidic soil to acidic groundwater, I think that there's a reasonable correlation between the fact that more than likely you're going to see or have prevailing low pH conditions in the southeast or northeast, because the surrounding soil and the matrix of the aquifer is going to be of a low pH. So you're dealing with fermentation, so you've got acidity produced and acids produced by fermentation. You've got acids produced by dechlorination. And finally, in some cases, depending on where your site is in the country, you may have prevailing low pH conditions that you have to overcome. So if you're considering doing bioremediation, you've got to address this. And so how do you do that? The common convention is to add a base or a buffer. Here I've shown 4 very common ones that are applied in situ. Everything from brucite or magnesium hydroxide to calcite or calcium carbonate. The thing I'd like to point out in this graph is the OH per kilogram column, kind of in the middle there right next to the pH column. And what this is just as our organic substrate and the amount of molecular hydrogen we get per pound of that substrate is important for dechlorination, for pH adjustment, the amount of alkalinity per kilogram or the amount of alkalinity per pound is important for our base to properly shift the pH of the system. So we would really want a buffer or a base that had a high alkalinity per pound or per kilogram. So you can see that magnesium hydroxide is the highest one of this set. The other thing I would call your attention to is the solubility column. You can see that while magnesium hydroxide is a very strong buffer, it essentially has 0 solubility. It's almost not soluble at all. If you compare it to something like caustic soda or sodium hydroxide, you're getting pretty good alkalinity and you're getting almost infinite solubility. But I'd like to go over some of these in detail and kind of weigh the pros and cons of using these beyond just alkalinity and solubility. First, let's talk about carbonates. So calcium carbonate, sodium bicarbonate, those are pretty typical buffers that are used for in situ bioremediation and pH adjustment. What makes carbonates an effective neutralizer or effective buffer to an acidic system, it is its ability to degas CO2. So that when you introduce sodium bicarbonate to an acidic system, what you're going to get is you're going to get sodium, you're going to get water, and you're going to get gaseous carbon dioxide. And that CO2 is going to need to effervesce, it's going to need to release to the atmosphere. And we see this occur, when you use something like Alka-Seltzer tablets, or if you have ever done the vinegar and baking soda experiment from grade school, you remember you get a very violent volcanic reaction, and that reaction is that degassing of CO2. If the system can't degas CO2, you sort of lose the effectiveness of the calcium carbonate or the sodium bicarbonate. So here I'm showing calcium carbonate now, and if that CO2 cannot degas, it cannot vent to the atmosphere, it remains in solution. The graph below is from a geochemistry textbook, and what it shows is as you increase the partial pressure of CO2, so as you add more CO2 to the system and it stays in solution, in regards to calcium carbonate, you're going to get obviously more dissolution of the calcium carbonate, so your calcium ion is going to increase. Your CO2 is going to increase. But what's going to happen is that because that CO2 can't go anywhere, it's going to remain in the system, and it's going to remain in that system and in solution as carbonic acid, not just as CO2 by itself. And so your pH of the system drops. Caustic agents like potassium hydroxide and sodium hydroxide, if you recall the table I showed a couple of slides ago, very strong alkalinity, and they have a very high pKa, or equilibrium pH, somewhere around 14. This is kind of a good or a bad thing. It's bad because it's very easy to overshoot the pH, or your target pH. And so you can easily shift the system from an acidic condition to an extremely alkaline condition and kill the aquifer. The other thing about these agents is they are hazardous. They are hazardous to human health. And so any health and safety plan that would utilize these materials is going to need to have the appropriate PPE and emergency medical and hazardous cleanup procedures in them. The final thing is that caustic agents like sodium hydroxide and potassium hydroxide, they're extremely soluble, almost infinitely soluble. This is a good and a bad thing. It's good because it makes it very easy to inject these materials into tight formations or just into the subsurface in general. But at the same time, that solubility makes them have essentially no longevity in the system. So once you introduce them, if there's any kind of groundwater flow in the system, you're essentially going to get a washout effect, and you're going to get no residual pH adjustment from these materials. They're just going to adjust, they're going to get washed out, and then you're going to be left with sort of a rebound of acidic conditions. So that brings us back to magnesium hydroxide. As I said, you know, it's a very strong base. It completely dissociates, so that's why you get that great alkalinity per kilogram. Its equilibrium pH is only about 10.5, so that means that no matter how much magnesium hydroxide you add to a system, the pH of that system is never really going to exceed 10.5. The interesting thing about magnesium hydroxide is that while it has a very low solubility, that solubility is directly controlled by the pH of the system it's in. So the graph at the bottom dictates this. The more acidic the condition, so the lower the pH, the more dissolution of the magnesium hydroxide you get. And of course, when you get more dissociation, that means you get more alkalinity. And so you start raising the pH, and when this occurs, then you start getting reprecipitation of the magnesium hydroxide. And so that if there was in a groundwater system, as you get up gradient to down gradient flow of acidic conditions or acidic groundwater, you essentially have this nice long-lasting effect that it will shift the pH of that groundwater as it comes into contact with the magnesium hydroxide. That pH will be shifted to an alkaline condition. The magnesium hydroxide will be able to reprecipitate in the location that it was injected into, and then as the groundwater flows out and more acidic water moves in, it's there all over again. So you get this sort of continuous cycle. So magnesium hydroxide has a very extensive life in the subsurface, a fantastic longevity, and a strong ability to regulate and control pH of a system. But, you know, as I said, the solubility is sort of the problem, and so what EOS has been working on for the last couple of years in our R&D department is coming up with a way to utilize all the benefits of magnesium hydroxide, but getting over that hurdle of that limited solubility. We want to be able to distribute this material in the aquifer effectively. So that's what led us to develop the product CoBuff MG, which is simply just a colloidal suspension of magnesium hydroxide. So the first thing I point your attention to is the specifications on the right side. This material, this CoBuff MG product, is going to be 45% by weight alkaline buffer, or magnesium hydroxide, and then a proprietary blend of dispersants and stabilizers. And this is what allows the material to stay suspended and distribute in the aquifer. So the first thing we did was we looked at the particle size distribution of the magnesium hydroxide grains within the product itself. And we saw that we were getting a mean particle size of right around 2 to 3 microns. So we were able to achieve a very small particle size distribution, so we knew we had a product that could potentially have a very effective transport capability in the aquifer, but we wanted to test this. So that led us to this experimental design where we passed the CoBuff MG product through a few sand-filled columns in the laboratory. We did this to observe its transport and its effect on permeability. The next thing that we did was we performed a titration to observe the pH adjustment capability and the stability of the product as in regards to being able to regulate pH of a system. The last thing was we conducted a small pilot scale study to observe field application of this product and how well it actually worked in a real world scenario. And for 2 and 3 there of the experimental design, we actually collaborated with a consultant. So this graph is from the sand-filled columns. This is the result of our transport experiment. So if you were to go out and buy magnesium hydroxide powder from just any supplier and mix it with water on site and then inject it into your injection locations, the result you could expect would be the blue line. That after a couple of pore volume flush of the aquifer, you essentially aren't moving the material anywhere. It's not going anywhere from that injection location, and we saw this in the column. We essentially got no measurable alkalinity on the effluent side of the column, and we kept flushing this column with more and more pore volumes. Eventually we got some of the material to start transporting, but not a whole lot, and in the end of the experiment we only got about 25 to 30% of the material to come out of the effluent side of the column, meaning that most of it was blocked up at the influent port. However, when we passed the CoBuff MG product through the same sand-filled column, we got the results of the red line. And you can see that just after the first pore volume flush, we were already getting above 10%. And as we kept flushing, we got up to 60% and then 70% until about the same time frame where we were getting just a little bit of effluent reads of the magnesium hydroxide water column. We were getting pretty much 100% of the CoBuff coming out of the column. So with this experiment, we were demonstrating that the CoBuff MG product has exceptional transport capabilities in the subsurface. Next is we wanted to understand what the pH control and adjustment mechanisms of the product were. And so for this, we got the help of a consultant, CB&I. They did a titration testing the CoBuff MG product on 2 different site materials from Fort Dix and from McGuire Air Force Base. And the starting pH of these materials were below 3. They added CoBuff in a titration experiment sequentially and then monitored pH, and the target pH was around 6. So from this graph you can see that they were able to achieve about a 6 pH with about 15 grams per kilogram of CoBuff aquifer material. But they wanted to keep going. They wanted to understand if the field technicians made a mistake and added too much, what would happen to the system. And you can see from this graph that when they added pretty much double the amount of CoBuff they needed to the system to get the pH they were after, the system never really got much higher than 8. In fact, it actually reached an equilibrium and leveled out. So we were able to demonstrate that not only is the material an effective pH adjuster, it's also very effective at controlling pH. You cannot sort of get this runaway effect that you would get from a caustic agent. Finally, we wanted to demonstrate the capabilities of the CoBuff MG in the field. And again, we got the help of CB&I. This was their project. They ended up injecting EOS LS, which is our low salt emulsified vegetable oil product that's an electron donor for dechlorination. They combined that with the CoBuff MG product to bring the pH of the system, which started around 4, to a more neutral range. They injected a mixture of the EOS LS and the CoBuff MG into 20 points that were installed on 5-foot centers. They injected about 69 gallons of dilute EOS LS with CoBuff at a 4% to a 0.75% ratio, and the rest of that solution would have been water. And then they got injection rates of about 0.15 to 0.3 gallons per minute, and it took them a little over 3 days to do this entire field project. The overall geology of the site is clay with interbedded sand, and they believe that the majority of the injectate went into those sand units. But that's okay, because that would also be the same units that would contain the majority of the dissolved phase contamination anyways. I'm sure you had some diffusion into the matrix media, but you can only treat those high K zones with a procedure like this. Last, the estimated groundwater velocity at the site was about 21 feet per year, so relatively low groundwater flow. Here's a layout of their injection design. The blue dots are the injection points. The black and the red dots, those are their monitoring locations. And the data that I'm going to show you in the next slide is from the center of this figure, from injection well 8, and then the subsequent monitoring wells, so MW1 to MW6. The numbers there next to it are the distance from injection well 8 in feet. So it starts at 2.5 feet, and then 5, and then 10 feet, and so on. So this is the results of the pilot test. So on the y-axis we have pH, on the x-axis we have distance from the injection well, or injection well 8, and then the different colored lines are different days that they went out and measured pH at all the locations. And what you can see is, from the baseline, the entire site was at pretty much a 4.5 pH all the way across the board. Once they introduced the CoBuff product and they went back out and they measured about 45 days after introduction, you saw that at the injection location their pH increased from 4.5 to almost 8.5. And then as you started moving away from the injection location, your pH started to drop, get back down into a more neutral, more acceptable range, until it got pretty close to baseline conditions, about 30 to 40 feet from the injection location. When they went out a third time, so 103 days after the initial injection of CoBuff and EOS, the pH of the injection wells was back down to around 7. And as you started moving away from that injection location, you saw the pH pretty much stabilize. There's a little bit of a drop there at 5 feet, but pretty much overall, from the injection location out to about 20 to 25 feet, you have neutral conditions. They were able to achieve a 6 standard unit pH, very far down gradient from the injection location. Something interesting about this is, remember, the groundwater velocity of this site is only 21 feet per year. So just in 103 days, they were seeing mobility out to, they were seeing a pH adjustment out to about 25 feet from the injection location. So this isn't a groundwater flow mechanism. This is just from the injection. This was their distribution they were able to achieve from the injection. So this here demonstrates that the material can effectively transport in the aquifer. Not only that, it has an extremely efficient ability to shift the pH of the system. So that'll pretty much wrap up my presentation. If you have any questions, please feel free to contact me. My contact information is below. As you are thinking about doing in situ bioremediation projects for your site, and you're interested in aquifer pH adjustment, I would urge you to strongly understand your site's soil and groundwater acidity. You could go out during your characterization and collect a soil and groundwater sample, submit them to a laboratory, and they can tell you the acidity of that material, so how much base you're going to need to add to adjust the pH of that aquifer. And that's going to be very important for calculating the amount of whether it's CoBuff or sodium bicarbonate or whatever you choose. It's going to be important to understand how much you need to add, and that number, that acidity value, will give you that that ratio you need, so you know how much material to apply. The next thing is definitely understand your contaminants of concern and what their concentrations are across the site. Do you have a possible residual source zone that you haven't quite mapped out yet? Is there any upgradient influence that might rebound the system? Do you have extremely high concentrations? Do you have something that's reaching the solubility limit and you're dealing with denapple phase contamination? All of this is going to play a part in how much acidity is going to be, or how much acid is going to be generated. The next thing is obviously the substrate you select, so the organic substrate that you pick. If you choose something like EOS, obviously you're going to get, it's a soybean oil based product, so you're going to get relatively low acidity. But if you choose to go with something that's more soluble like sodium lactate or molasses, just understand that when that material ferments, it ferments very rapidly and is going to release acids very rapidly, and that could be a problem for the system. I appreciate everyone listening today. As I said, if you have any questions, please feel free to contact me below, and have a great day. Thank you so much for listening.